Welcome back. I'm going to go through another of the problems of the test, which I think will be helpful going forward. Here is there was a truck problem with a spring and a scale. I think most people did okay with that one. But then we got this nice pressure transducer. So now I have an electro system that, okay, we're just trying to see what the uncertainty is. So we weigh our truck. We've got a pressure sensor. The range increases to 100,000 kilograms, which corresponds to 6,500 kilopascals. It goes through an active filter, as it shows. Then it switches positive to negative. Then we get to our digital display. And here is some of the important stuff. So we've got three different stages. Pressure transducer, supply voltage of 12 volt DC. Does that matter to us? No. I need to power it. So if we were running a lab, yes, that's important. But as to our uncertainty, that doesn't change it. The input range is up to 6,500 kilopascals. Output is 0.5 volts at maximum. And it does read 0 with no load. We've got accuracy. We've got thermal drift. Now, what are we reading here? The digital display reads 21,960 kg. So using that, we can kind of work our way back as to what are some of the voltages going on, so we can set it up that way. Now, some of you may put everything in terms of kilograms. That's fine. Some of you might do it more in terms of volts. That's also okay. But the amplifier is that can be tricky. So that's why we're going over it today. So digital display reads 21,960 kg. Let me just put that here. 21,960 kg is our output reading. So we have the transducer here. Box. It goes through a filter. And then it goes to the digital display, and that's what's being read. And this gives us increments of 10 kg. So what I want to find just right off the get-go is I want to find what are some of these voltages going on here. So we can work our way backward. That's fine. We can try to work our way forward. Doesn't really matter. For the digital display, the input range is 0 to 10 volts, and the output is 0 to 100,000 kilograms, smallest increment being 10 kilograms. So what does that mean for my voltage? Well, the input to it is 0 to 10 volts. The output can go all the way up to 100,000 kg. And we're somewhere right here because we're at 21,960. So what is that voltage? Well, you can probably do the math in your head. It's not too hard. This is going to be 2.196 volts. If it is kind of hard, that's okay. But you find the sensitivity. So output over input, 100,000 divided by 10, basically 10,000 kilograms per volt. That's how we can get our voltage right there. So that means that coming out of the amplifier, it's 2.196 volts. This is interesting because when I look at the active filter, so now I've worked back to the active filter, and it tells us it's going to have some cutoff frequency. It's a low pass filter. It tells us supply voltage, which doesn't really affect us. And the uncertainty is negligible. That's great. I like that. But it doesn't give us what the gain is. So now we kind of have to figure that out. So let's skip over that. We have our input for the pressure transducers up to 6,500 kilopascals. How do I find the actual, what are we reading here? So if I'm at, this is 21,960, we're trying to figure out what is the kPa that we have to deal with. So again, this is looking a little bit at sensitivity. And in this case, the Do I have the math on this? Let's find out. Well, I can do 6,500 divided by 100,000. That gives me a slope of 0.065. If I multiply that by 21,960, I get 1,000. This is 1,427.4 kPa. Okay, so using that number, I can figure out volts. So this goes up to 6,500. So I can multiply that out, and based on the range here, so I'm about 1/10 of the way up, we get a voltage output of 0.1098 volts. Okay, so again, here's my transducer. This is 1,427.4 kPa, which corresponds to the 21,960 kg. And again, I can look at a bunch of different ways. I can put everything in terms of kg. I'm going to choose to do it in terms of volts, but there were different ways that you could go about doing this. Now I can actually figure out what my gain is. So if I take 2.196 output voltage over the input voltage, that actually gives me a gain of 20. That's going to be helpful there was a part after this where you each wanted to figure out the resistors to use in the op amp. Now I know my gain is 20, so I want R2 20 times as large as R1. Okay, how you doing? You doing okay? So now that I've got those voltages, I think that's helpful because now I know, the voltage coming out of here. So the first step, I'm going to do this on the next page. I'm going to figure out the transducer. That's going to have some uncertainty. I can look at the active filter. Thankfully, uncertainty is negligible. Now, the uncertainty of the transducer still will get amplified, so I don't want to forget about that. And then lastly, we're going to cover this. So we've got some uncertainties here, even just based on the resolution. I don't have to worry about the supply voltage. That's just powering it. It's not going to contribute to the uncertainty, only if it was really specified that that does play a role. And so we're going to go to the next slide and cover some of these things and then ultimately put them together with the root sum square. So here we go. The goal is to find what is the uncertainty at this value. It doesn't meet the error requirement of 500 kilograms. So I'm going to put in some guardrails, and here we go. So this is for the transducer. So we have accuracy. This is, you can scroll back through it, 0.32% times my reading, which is 0.1098 volts. Again, I'm going to do volts. You could have done kilograms, that's fine. Even kPa, whatever kind of works. You can always transfer kind of between the two. There was also thermal drift, and this one did not have anything to do with degrees Celsius. If I go back, like I know it says thermal drift error, but if I'm looking at that, it only says percentage of the full scale output voltage. So therefore, I don't need to know the temperature. This is just going to be 0.0022 times, this is the full scale, which goes all the way up to 0.5 volts. And so this is equal to 1.1 millivolts. And so we can really quickly find the transducer uncertainty. That's going to be the combination of 0.351 and 1.1. And this is in millivolts. It is 1.155 millivolts. So that's for the transducer. But we're not really finished, because that goes through the amplifier, and we know that the gain is 20. And so the output voltage is equal to gain times the input voltage. Thankfully, the gain has no uncertainty, so it's not a multivariable problem. But for my output voltage, so I could say U amplifier is going to equal gain times the uncertainty of that input voltage coming in, which is coming from the transducer. And so this is equal to 20 times that 1.155 millivolts, which equals 23.1 millivolts. Okay, so it does, again, if I have small differences in the transducer, that's going to get amplified. And so I want to make sure I've got that here. Again, you could put this in terms of kilograms. If you do that, it may save you some headache. But either way, we do see a sizable change. The transducer is not going to really affect too much of this. Unless we have that amplifier, which we do. So the last step is the digital display. So we're trying to find the digital display uncertainty, and there's a few things going on. First off, it is digital. We want to look at the zero order uncertainty. So this has an uncertainty of 10 kilograms. That's the resolution. So if I want to change it, you didn't have to do it, but I'm going to change it all to volts. So looking at my digital display, there's 10 volts for every 100,000 kg. So this gives me 1 millivolts. Pretty nice. Then there's accuracy. Accuracy is 0.15% times the reading, which is 2.196 volts. So that is 3.294 millivolts. Again, you could use the 21,960 kilograms. You put it all in kilograms, that's totally fine. One maybe confusing one, if I go to the digital display, is the last one, linearity error. This gives you 0.13 millivolts over the input range. So there's actually not a percentage, anything. I don't want to multiply it. I just want to keep it as 0.13 millivolts. And so if I scroll up a little bit, all of these are in millivolts. So now I can find the digital display, which is all of this. We have 1 squared, 3.294 squared, 0.13 squared. And this gives me 3.45 millivolts. All right. So I've got the 3 different stages. Now, as you can see, transducer, it's very small, 1.155, and really that goes through the amplifier, and so that's kept here. So if I want to look at my total design stage uncertainty, it's really just what's coming out of the amplifier. So 23.1 millivolts and the 3.45 millivolts, that is the uncertainty at the digital display. And this gives me, as I show I'm not exactly prepared, this gives me plus or minus 23.356 millivolts. Okay, and you know, if I included that transducer, that wouldn't change it by hardly much. And again, the amplifier uncertainty is what's based off of that, because it's just gain times that uncertainty. So now I have this. This can be translated to, and this is post amplifier. So everything's post amplifier at this point. We multiply it by 100,000 kilograms per 10 volts. And that gives us our answer, which is plus or minus 233.6 kilograms. So that is our uncertainty, which is less than the regulation of 500. And that's how I did it. So just approaching the problem, trying to do each one individually, I like to kind of map out what are some of those voltages, what are we dealing with? And then at the end, make sure we combine it. And even though the gain did not have any uncertainty, it did contribute by amplifying the uncertainty of the transducer. So I hope that was helpful. Bye.